My name is Avi Gupta and I'll be presenting our work titled Co-Saliency Inspired Referring Camouflage Object Discovery. In this work, we propose a novel setting of referring camouflage object discovery. Let's look at the image here. We have a pool of camouflaged images and a referring image of a frog. Our proposed network CIRCOD aims to search for the object from the referring image within the pool of camouflaged images and further segment them if found. Some of the applications in representing the setting are in discovering cysts or polyps in medicine, visual object search, military operation, aerial search and rescue, and many more. However, this setting in a complex scene like camouflage comes up with challenges too. Camouflage scenes are difficult to discover due to the visual complexity of objects as they blend within the environment. But if we have an additional help in the form of reference image that can provide the required knowledge to segment the object of interest. Another major challenge is the large visual disparity between the camouflaged and salient referring images. Finally, there are out of distribution challenges where the model learns on certain categories and evaluate to different other set of categories. The main idea is to leverage the concept of co-saliency to discover the camouflaged object. It has primarily two parts: co-saliency aware image transformations and co-salient object discovery. We will begin with co-saliency aware image transformation. There are two transformations in this part. First, the saliency enhancement network, and second, the image alignment network. As mentioned before, objects in camouflage image are indistinguishable from the background, so we try to enhance the camouflaged image using the saliency enhancement network. Further, we have tried to minimize the structural variation between the enhanced image and the referring image by aligning the latter. We will be seeing further explanation on these two in upcoming slides. This is a framework for both saliency enhancement network and image alignment network. To enhance the object from its background, negating a background is necessary, which will make the object boundary more evident. To achieve this, a preliminary object mask is necessary. We pass the camouflage image through this encoder-decoder based network to get that preliminary object mask, identifying all the objects in the frame, which is processed with the input image to finally get the enhanced camouflage image. As for the alignment network, we take the previously enhanced camouflage image and use that to align the referring image to minimize the structural variation between the two. The equation here explains how the input camouflage image and its preliminary binary mask are used to create the enhanced image. The image is multiplied with its mask and added to the product of their inverse. This negates the background and makes the object more evident. The figure shows the input camouflage image, predicted binary mask, and the enhanced image. The objects are much more clearer in the enhanced images. To obtain the predicted binary mask and enhanced image, we train our salience enhancement network and use two loss functions to learn the gradients: pixel position aware loss for predicting the mask and mean squared error loss for minimizing the difference between the enhanced images. As for aligning the referring images, we use a pre-trained test correspondence model. We create the estimation matrix which is used to align the referring image. After achieving the transformed images and reducing the visual disparity, we leverage the idea of co-saliency to discover the camouflage object using the referring branch. In the further part, the network processes these two transformed images first by jointly extracting the features, then computing joint attention, and finally predicting the similarity and eventually discovering the object. We extract the joint features from both the branches using a pyramid vision transformer. The extracted features are passed through a combination of joint channel and spatial attention to finally get the attended features. The extracted features are first passed through joint channel attention. The features are summarized spatially across the channels in both the branches and are computed together to finally receive the common weight vector, which is multiplied by the original extracted features. These channel attended features are further passed through joint spatial attention. The features are summarized channel-wise to finally receive a matrix of one channel each in both branches. These matrices are computed in a similar manner as joint channel attention and multiplied with previously attended features to finally receive the jointly attended features. These attended features are then passed through two modules to segment the object and predict the similarity respectively. Firstly, These two features representations are passed through combination of self-attention and cross-attention to yield the segmentation mask. Simultaneously, those two representations are passed through prediction module to receive the probability value, which identifies whether the object in both the branches are same or not. Here we show the loss function to train the network. There are two main losses, detection loss and camouflage object segmentation loss, and one auxiliary loss, referring image segmentation loss. To support our idea, we propose a new dataset called ref1k, which consists of 1000 plus referring images divided among 5 classes and 76 categories. These categories are the union of all the categories present in the current benchmark camouflage datasets. We also present three major settings in our work. CORD setting, where we evaluate the unimodel approach to just segment the camouflage image, which we compare with proposed SEN. RefCOD setting, which is a referring based approach considering only positive samples, and RCOD setting, which is a referring based approach considering both positive and negative samples. Here are the results from our conducted experiments under CORD setting for three benchmark datasets. Our proposed SIN has comparable results to proposed to SOTA methods, but it is important to note that SIN is not our final outcome but only a side product. These are the visual results in CORD setting. Here we see the experiments in RefCOD setting. As seen, our method surpasses previous methods by a certain margin. This table represents the experiments conducted in the RefCOD setting covering auto distribution scenario. We train the network on 3 out of 4 major classes and test on the remaining mentioned one. These are the visual results in our COD setting. These are the two sets of experiments in our COD setting. Table 4 shows our proposed CIRCOD with large generic referring based methods, while Table 5 shows the evaluation studies we perform, checking the effectiveness of our modules on Code 10K dataset. Thank you.